Welcome back. Today, we're diving into an incredibly fast-paced, high-energy crash course. We are taking the absolute core fundamentals of Class 10 science and packing them into one logical, highly visual explainer. We're going to travel all the way from the invisible, microscopic atomic level, straight through the biological engine of the human body, and finally zoom out to the vast, macro-level rules of physics that govern light itself. So let's get right into it.
Here's our roadmap for today's explainer. 1. Chemical reactions and equations. 2. Acids, bases, and salts. 3. Human life processes. And 4. Light, mirrors, and lenses.
Starting with part 1, chemical reactions and equations, the micro foundation.
Okay, so the absolute bedrock of chemistry comes down to 4 fundamental interactions. First up, we've got combination reactions, where simple substances combine to form one single compound. Then, naturally, the exact opposite, decomposition reactions, where a compound breaks down into simpler elements. Next are displacement reactions, where ions literally swap places to form entirely new substances. And finally, oxidation, reduction, or redox reactions. Think about how carbon acts as a reducing agent to remove oxygen from manganese oxide, right? That oxygen transfer is the whole defining characteristic of a redox reaction.
And this perfectly illustrates the step-by-step logic required to balance a chemical equation. You see, because of the law of conservation of mass, absolutely nothing can get lost in chemical translation. Take a look at this reaction where iron reacts with water. We don't just guess here, we follow a strict order. We balance the metals first, so making sure we have exactly 3 iron atoms on both sides. Then we move to the nonmetals, and finally, we tidy up those hydrogen and oxygen atoms. It's like a perfect mathematical puzzle, just at the chemical level. Now let's talk energy transfer. It's fascinating to contrast endothermic processes with exothermic ones. Exothermic reactions, as you might know, release heat into their surroundings. A perfect everyday example, human cellular respiration. It's exothermic, constantly releasing energy, but it's carefully regulated by our bodies so you don't experience a sudden, massive spike in your body temperature. On the flip side, endothermic reactions, like decomposing organic matter into compost, actually have to absorb heat from their environment to just proceed.
Moving right along to Section 2, acids, bases, and salts, chemical properties.
You're probably familiar with the pH scale, ranging from 0 to 14, and how a universal indicator shows different colors for varying concentrations. But here's a mind-blowing fact from our source material. When the pH drops from 4 to 2, the hydronium ion concentration isn't just doubling. No, it's actually increasing 100 times over. It's that massive, exponential shift that forces the indicator paper to dramatically change its color to a deep red.
But hey, color isn't the only way to detect an acid or a base. Have you ever heard of an olfactory indicator? This is a substance whose smell actually changes depending on its chemical environment. Say you need to test for bases, but you're completely out of pH strips. You can literally use onion juice. It's wild, but onion juice will completely change its smell when introduced to a basic solution, while in an acidic solution, its characteristic odor remains completely unchanged.
Let's organize some essential, everyday salts that are formed through these chemical reactions. We've got bleaching powder, which is absolutely vital for disinfecting our drinking water. There's baking soda, which reacts to release carbon dioxide. That's what makes your cakes wonderfully soft and spongy. And a really fascinating one is plaster of Paris, or calcium sulfate hemihydrate. Notice how it requires highly specific dry storage. That's because if it absorbs even a tiny bit of moisture from the air, it triggers a chemical reaction that turns it into hard, completely unusable gypsum, so keep it dry. All right, zooming in on ourselves now. Section 3, human life processes, the biological engine.
Tracing the human alimentary canal shows us exactly how food is systematically transported and chemically broken down. It's essentially a continuous, highly efficient assembly line. But the absolute most critical chemical exchange happens right at step 4. If digestion and absorption in the small intestine were to fail, vital nutrients would never make it into the bloodstream. And without that assimilation, your body's cells are completely starved of the chemical fuel they need, which quickly leads to critical weakness. Speaking of fuel, our bodies have to adapt chemically during intense physical exercise. Under normal conditions, we use aerobic respiration, taking in abundant oxygen to fully break down glucose for maximum ATP energy. But say you're sprinting and oxygen runs low. Your cells are forced to instantly shift to anaerobic respiration. This backup process yields significantly less energy, and as a byproduct, it produces lactic acid. That rapid buildup of lactic acid,
That's exactly what's responsible for those painful muscle cramps you get during a heavy workout. Now, the human double circulation system is just an absolute marvel. Because we're large multicellular organisms, simple diffusion just isn't going to cut it for getting oxygen to all our cells. We desperately need this robust dual pump system routing blood through the heart and lungs. And because this organ pumps with such incredible force, our arteries are structurally designed with very thick, highly elastic walls. That biological engineering is absolutely necessary to safely withstand the intense, high pressure of blood being forcefully pumped straight out of the heart.
And, well, just as the body takes things in, it has to expertly filter them out. Enter the nephron, the microscopic functional unit of our excretory system, located right in the kidneys. These little structures work tirelessly, filtering waste, specifically urea, excess salts, and water, straight out of your bloodstream. If these nephrons were to fail at this vital filtration process, those wastes don't just magically disappear. They quickly accumulate, severely disturbing the body's delicate internal chemical balance in a way that can be instantly life-threatening.
Finally, let's zoom way out. Section 4. Light, mirrors, and lenses. The macro world. So image formation is based on incredibly strict geometric rules. For instance, if we place an object precisely at the center of curvature, point C, in front of a concave mirror, the light rays converge and reflect in a very specific way. The resulting image is real, inverted, upside down, and mathematically the exact same size as the original object. It's absolutely brilliant. And these aren't just suggestions, they are the precise mathematical rules governing light. The angle of incidence always exactly equals the angle of reflection. But here is a truly fascinating one. If you rotate a flat plane mirror by just a few degrees, the reflected ray of light actually turns twice as much. And when we look at refraction, any ray of light that passes directly through the exact optical center of a convex lens is going to emerge completely straight, without bending or deviating at all. Understanding those exact rules allows us to manipulate light purposefully, which brings us to the power of a lens. This is a crucial measurement of a lens's optical power, calculated directly from its focal length, and we express this value in a unit called diopters. So for example, if a student conducts an experiment and finds a convex lens creates an image at a specific calculated distance behind the lens, they can yield a specific power measurable in diopters. And guess what? This is the exact math your eye doctor uses every single day to engineer the corrective lenses in your glasses.
Well, having mapped this incredible journey from the step-by-step balancing of microscopic atoms through the vital chemistry keeping your heart and lungs pumping, all the way to the unbending mathematical physics of light, I want to leave you with a question. How will you observe these fundamental forces at work in your own life today? Science isn't just trapped in the textbook. It's the highly structured reality happening right in front of your eyes. Keep observing, keep questioning, and I'll catch you in the next explainer.